And my name is Akane Sano at Rice EC Department. Welcome everyone to join our first health seminar series. Today we are very excited to welcome Professor David Kotz at Dartmouth College. And Professor Kotz is one of the leaders in mobile health research, and I have been following his work. Let me introduce Professor Kotz a little bit. Professor Kotz is a Rosenwald professor in the Department of Computer Science, Dartmouth College, and he is currently a visiting professor in the Center for Digital Health Interventions at ETH Zurich. He previously served as interim provost, associate dean of the Faculty for the Sciences, executive director of the Institute for Security Technology Studies, and he was also on the U.S. Healthcare IT Policy Committee. His research interests include security, privacy, pervasive computing for healthcare, and wireless networks. And he has published over 200 referred papers and also obtained over 80 million grant funding and mentored nearly 100 research students. He is a fellow of IEEE and a distinguished member of ACM. So we are very, very excited to learn about his research. And just before we start, I wanted to let everyone know that if you have any questions, so we have a Q&A box on Zoom, so you can see it at the bottom of the Zoom window. So feel free to type your questions in Q&A box. And you can also raise hand. I think there is a button on Zoom. Okay, then I will hand our microphone to Professor Kotz.
Well, thank you, Akane, for inviting me and for that very nice introduction. It's great to be here at Rice. Never actually visited Rice, and I guess still haven't, but I hope I will at some point in the future. I'm planning to talk about a variety of projects that are recent or underway or planned at Dartmouth around this theme of mobile and wearable technology for computational well-being, and I absolutely would look forward to your questions or feedback. I'm going to start with a very quick overview of what is mHealth, because it's one of those buzzwords that everybody uses, but maybe has a different definition. And then I'll talk about 4 different projects: Amulet, Oracle, Simba, and Detect, roughly in that chronological order, actually. So mHealth, as I mentioned, is a buzzword. Lots of people use it. Here's what I mean by it. It's the use of mobile computing or communications technology either to deliver healthcare or to collect health information for research, for example, or public health. And the kinds of devices that are available for mHealth are widely varying and emerging all the time. It seems like a new gadget every week. Some of them as simple as a smartphone, of course, is an mHealth device, but also other wearable or usable devices, some of which are FDA-approved medical devices and some are more consumer-oriented devices. And not all of them are personal devices. They might be shared by several people in a household, such as a bathroom scale, or even an environmental monitoring device like temperature and humidity, which matter for certain kinds of health conditions. So with that, I'll dive into the first project that I want to talk about today, which is Amulet, in which we started about 8 years ago to think about how you could build a platform on the wrist that would provide mobile health application capabilities. And at the time, there were wristbands, fitness bands, really single purpose devices that you could wear on your wrist that would count steps and things like that. And then there were just at the beginnings of the smartwatches, which are much more capable. You can run multiple apps, but they have terrible battery life, maybe a day or something like that. And we were interested in something in between, right? Something that would not have the shortcomings of a closed platform, fixed purpose platform, and not have a short battery life like a smartwatch. And so the Amulet project was born. The name is a word, and it means sort of protection from disease or danger, and we thought that might be a nice name for the project. So here's what it looks like kind of at the big picture. Here's a patient or a person whose health is of interest at the bottom, and he is wearing various sensor devices or medical devices on his body and also an amulet on his wrist. which can have applications and communications to work with those various devices. And when the smartphone is available, and we anticipated it's not always available, then that amulet has a pathway to the cloud for its data, or it can download from the cloud new apps or new controls, new configurations from the cloud. And we imagined that those would be provided by, or at least prescribed by, clinical staff or health coaches or something like that. So our goals for the Amulet as a project was to support multiple applications, but with strong security, to have long battery lifetime, and to have tools for developers to enable them to achieve long battery lifetime, and also to be usable by everyday people. This is not a gadget intended for techie people, and ultimately open source, which it is now. And so this is what the Amulet looks like today. We went through several prototypes, of course. It's a 3D printed case and some electronics, and I'll talk about very briefly about some of those. There's too much to say, considering I also want to talk about several other projects today. In the end, we developed a variety of applications, some for just demonstration purposes to test out the capabilities of the Amulet, and some that actually became the basis of some medical studies, and particularly around stress. In the first case, that was I'll talk a little bit more about that later. We ended up using the Amulet in 11 different studies, some very small, like you can see the first one is just n equals 2 participants, and some larger, up to 40 participants, with many hours of data collected from EMA, which is ecological momentary assessment. So that's asking the user some questions and getting multiple choice responses, and we allowed them to use the Amulet for that purpose. Activity sensing, meaning accelerometer and gyroscope, basically. Heart rate sensing. The Amulet itself does not have a heart rate monitor, but has Bluetooth, and it can talk to standard heart rate devices. Our interval, which is also heart related. EDA is, I'll talk about later. Step counts, and force on an exercise band, I'll talk about that. So one example of an application we called Geriactive, and this was designed with from the motivation of a colleague of ours, a physician who treats older adults and who wants to monitor the activity levels of older adults and to encourage them to be more active. And we found that the models that we had developed for younger adults just weren't useful for older adults. And so a lot of this project was in designing models and validating models specific to older adults. And I mentioned EDA, which is electrodermal activity, or sometimes called GSR, galvanic skin response. That was another device that we built, also wrist-based, in the Amulet project. And in this one, you can see in the photo a board on a coin. That's a custom board built by a student to measure electrodermal activity, the skin resistance, and we use that in stress studies. And he designed it specifically to fit into a Fitbit wristband, which are cheap. You can buy empty bands quite easily, and you can see that also in the picture. And then we were also interested, again, with that physician who treats older adults, in measuring their compliance with and their success with daily exercises. So he would send his patients home with a Theraband, which is a brand of exercise band, and ask them to do certain exercises, like in this picture here. And he was interested in knowing remotely whether they did those exercises, whether they did them correctly, whether they did them with enough force, and whether they were therefore building the strength that they were aiming to build. And so we modified the handles of some Therabands to include a force sensor, a pressure sensor, and Arduino, basically, to read that sensor and transmit it over Bluetooth. And you get signals something like what you see on the right. And then through some analysis of those signals, we can count the repetitions, and we can measure the amount of force, and ultimately the total kind of workout strength, if you will, of these older adults. So that was a very quick tour of Amulet. That project is basically over at this point. We're still publishing some of the final papers, but if you're really interested in learning more about it, go to amuletproject.org, and you can get all of our papers, including full-length video talk like this one, and also Mobicom paper that was presented last fall was about our experience in developing, designing, and using the Amulet over several years. And that video of that presentation is also available there. As I mentioned, it's all open source, open hardware. So if you want to build your own or program some for it, great. We'd love to hear about it. So the next project I want to mention is Auracle. This one is ongoing. And here the goal was to measure eating, really to detect eating behavior. The challenge came to us from researchers who study eating behavior. And they said, you know, we have all these gadgets that measure or estimate caloric output, you know, how many steps you took somehow translated into how many calories you burned. But we have no good way of measuring caloric input, basically how much you eat. And so we decided to try to solve this problem. And of course, the full problem is very difficult. A lot of people have worked on it, but to be actually measure how many calories you intake is not possible today with our technology. But we started with the basics. Are you eating? So we wanted to build a device, a wearable, head wearable device that would detect that you're eating. And then you can extract things like when you eat, how long you eat, and with help maybe from a smartphone, where you were, whether you're with other people, etc. And that's data that today's eating behavior researchers just don't have. So we built a device that was a custom board plus a 3D printed frame. Well, actually on the left there is a hacked up set of headphones that over the ear behind the head headphones that we cut off and made into a frame. But then we 3D printed our own, as you can see in most of the slide, in order to fit the electronics and the microphone. So our approach is to use a contact microphone. And I'll talk a bit more about that in a minute. Our more recent prototype is actually just a headband, a sweatband. Just go to the athletic store and buy one of these elastic bands, and then we sew a little pocket into the side of the band and for our electronics. And this has a lot of advantages. It's expandable, and we did a study recently with children, and it was hard enough to do the study with adults, but with children, their heads, of course, vary dramatically in size, and they don't like the uncomfortable plastic. And so this has turned out to be more practical. So as I mentioned, the key sensor is a microphone. We did experiment with other sensors, in particular EMG, electromyography, measuring the signals, electrical signals of the jaw muscles. But in the end, that was really awkward to install and remove from every subject, especially if you want them to go out into everyday life, which is our goal. So this is a standard off-the-shelf microphone that has a little rubber pad, and it senses sound only in contact with a device or a surface. And in this case, that surface is the skin behind your ear. There's a hard bone there. If you press on it, you'll easily find the mastoid tip. And when you're chewing, the sound of chewing transmits very cleanly up through the jaw and into that bone. And then with the microphone in contact, you could easily pick up the sound of chewing or speaking or coughing or what have you. And so our device, as you saw, is pretty clunky. It's pretty big, but the idea was that it would be maybe eventually as small as a hearing aid and would be behind your ear and out of sight. So that means we're picking up audio, and we basically, actually we're only sampling at, I think, 500 hertz, and we really are only interested in the 20 to 250 hertz range. Chewing is a very low frequency activity. And so this, I won't go through the whole data pipeline. It's pretty standard. You know, we take the raw signal, we do some downsampling and some band filtering, and then we extract features and we classify it as either eating or not eating. But the more, maybe an easier way to see that is that we have a two-stage approach. Most of the time, people are not eating. And in fact, most of the time, they're just silent, right? So the very simplest first stage is a simple, essentially, amplitude threshold. If there's appears to be silence in the window of interest, then we just ignore it. But if it appears to be not silence, then we put it through our classifier. And we experimented with a variety of different classifiers and found that the LR classifier, logistic regression classifier, worked the best. And as you can see here, we ended up with an F1 score of about 77%. And this is in the field. So We actually put this device on people and sent them out to do whatever they would normally do, and asked them to, eat at least once during their, I think it was 2-hour period of time. And, and then we would collect ground truth data and compare that with what our models were predicting. Now, I realized that I did not tell you how we collect the ground truth data. I should have included a slide for that. We modified a baseball cap that has a brim, like most baseball caps, and to put a camera in the brim pointing down at the face. And so we have this video for 2 hours when they were out in the real world. It's a very weird video to watch because all you see is their face. And so we paid some people to actually watch that video and to count for every second whether that person was eating or not eating, and use that as the ground truth. So here's another way to look at the performance of the LR classifier. And you can see again that F1 score of 0.78. And this is for a 1-minute time window, meaning we took a 1-minute period of samples and we ran the classifier over that. And so we get a result for each minute of the day as to whether they were eating or not eating. And in the plot on the right, you'll see the x-axis reports the number of features that were used by the classifier. So of course, using standard methods, we can generate hundreds of features using a package like TSFresh. And not all those features are useful. So we used feature selection algorithms to down select the features that were most useful. And so the top 5 or 10 or 20 or 50 features in that ranking could be used for classification. And this plot shows the accuracy, precision, recall, etc., for those different numbers of features. And you can see that after about 40 features, the metrics all more or less level off. So we decided that using 40 features with the LR classifier, using those 40 features with the LR classifier was the way to go. So to kind of summarize Oracle, we have now a device that can do eating detection in the wild pretty well. Of course, we will try to do better. I didn't talk much about eating episodes. What I just reported were minute by minute eating results, classification results. But if you think about yourself as an eating researcher, somebody who studies eating behavior, you probably don't care about every minute of the day. What you really want to know is, okay, how many meals did they have? And how many snacks did they have? How long were those meals? We call those episodes. And we then try to detect episodes. And really, that's just a matter of aggregating minutes where you're mostly eating for some period of time. We call that an eating episode. And we were successful in detecting 20 to 24 of those episodes out of 26, depending on which metrics you look at. And that's pretty good, but we'd like to do better. Battery life actually has not been a problem, at least with the battery that we've been using. 28 hours is good. Our goal is 18 hours. The idea is you would wear this device throughout the waking day and then charge it overnight. So this team is actually quite large. This picture doesn't even include everyone involved. And there's other activities going on. And there's an HCI group who's interested, for example, how would you interact with such a device? So a wrist device, you might have buttons or a touch screen, but a head device, you're not going to have a touch screen, of course. And so they're interested in gestural interfaces, what kinds of interfaces people would be willing and able to do, and what kind of interfaces can we actually build sensors to detect. And then there are some who are interested in the low-level electronics, and in particular, Kofi Odame, a Thayer School professor, is developing analog versions of these classifiers to be ultra small and low power. That project is continuing, and you can go to oracleproject.org to see more details. An even newer project then is something we call Simba, and it started in the Amulet project, and I'm only going to be able to talk about some of it today. But the first piece I will discuss is detecting stress. So I mentioned that the Amulet project wrote some applications to detect stress, and I'll report on some of those results. The broader picture of Simba is kind of aimed at the broader life cycle of sensing and intervention. So if you think about where most of the work so far in our community, the computer science and engineering community, has been about sensing. How do you sense information about people and infer something about their behavior or their physiology or their health? But then ultimately we want to turn that information, those inferences, into action. And so that's where our clinical or psychological colleagues come in and can design or provide interventional methods. So given this sensed information about the person, we want to turn around and deliver some intervention to change their behavior or to help them manage their health. And so that leads to a question then, okay, well, when do you deliver that intervention? So the algorithm may detect some condition, either of the person or the environment, that triggers it's time to deliver this intervention. But it's not always convenient. For example, I frequently have my watch tell me it's time to stand when I'm sitting on an airplane or driving a car. And I'm sorry, I just can't stand right then. So I need these algorithms need to be more thoughtful, if you will, about when to deliver interventions. And then kind of the next step is then, well, how do you deliver that intervention? And of course, many people have several devices, a laptop, an iPad, a smartwatch, a smartphone, or even ambient home devices that all are potentially a mechanism for communicating with the person and telling them or asking them to conduct some sort of intervention related activity. And that's that's a stage that we'd like to get to in the next year in the Simba project is after we've been studying these other parts, how can we optimally choose the right device to deliver that message? So you can sort of boil this down to what, when, and how, what is going on with the person or her environment, when do we deliver the support, and how do we deliver it? So one of the first parts of the Simba project, as I mentioned, was focusing on stress detection. This is the what, right? Trying to sense the current physiological condition of the person. And our interest is in doing it with just off-the-shelf hardware, in particular the Polar chest-mounted heart rate monitor. It's commonly used by runners and so forth. A lot of the prior work in stress detection used custom-built hardware that had multiple different sensors that you would wear on your chest or other parts of your body. We wanted to see how well we could do with just a simple device like this. And so within the Amulet project, and I'll tell you a bit more about the experiments, we recruited a set of subjects and we did both lab and field tests with them. So in the lab, we gave them a set of stressful experiences at times that we can control. And so we know exactly when they should be experiencing stress, and we measure the physiological response. So now we have the ground truth, which was our induced stress periods, and the sensor signals that we can classify. In the field, of course, it's a 3-day free living condition. We don't know what was happening to them, but we did prompt them with EMAs, like ecological momentary assessment questions, to ask them how stressed they feel and get a sense of the ground truth. So on the bottom in this timeline, you see the lab study. So they came in and they rested for 10 minutes, and then we asked them to do complicated math for 4 minutes. That stresses most people. And then a 5-minute rest, and then we asked them to just sit quietly while we snuck up behind them and dropped a big book to startle them. That generates a stress response, and then a rest. And then you put their hand in ice bucket for as long as they can stand it, and that generates physiological stress too. These are standard tests and all IRB approved, just so you know. And anyway, this is a very typical way to evaluate stress algorithms in the lab. In the field, then, we sent them out with an amulet, which we used for the EMA. It was not, in this particular experiment, collecting sensor data. So we have a pretty typical data pipeline here. Again, the raw signal is coming in on the left, and we clean the signal, try to exclude physical activity confoundments, and then clean up the data, normalize segment, and compute features. And of course, you can produce lots and lots of features, and again, rank them by their value for inference. And then to kind of cut to the chase, here's our results on the left. This is the F1 score for our approach in light blue, and precision and recall in dark blue and gold, respectively. And then the two other groups are C-stress, which was a paper from Santosh Kumar's group back in 2015, which is kind of the state of the art in terms of research capabilities. Again, that was a custom device with lots of sensors. And so we were pleased that our F1 score at least was pretty much the same, and all we were using was a $60 heart rate monitor. So that was great, but we were hoping to do better. And so this is like so many of these things, it's chunking time into windows, and then you're running the classifier in each window and producing a result. And then you compare that against the ground truth and you compute your metric. Well, most people are not stressed or unstressed on a minute by minute basis, right? Stress tends to come in and then fade over time. And so we chose to use a Bayesian network model that incorporates the stress result from the prior window as another feature, in effect, in predicting the stress for the current window. And so that, given that our models output a probability of stress, we can use that output as the input into the next window's Bayesian model. And that allowed us to improve significantly. We've added this second grouping here. This is the polar H7 two-layer model, like I showed you. And it's raised our F1 score up to, I guess it's about 0.87. And it's significantly better than C-stress. So that's all I'm going to say about Simba today. There were some other interesting research on receptivity. That was that sort of when question that's just coming out now. And again, I'm happy to talk offline about that. But let's move on to the fourth and final project, which is really just getting going in some ways, and that's called DETECT, which is a short name for a very long named project, which is all about opioid use disorder. So I imagine you've probably read about this in the papers. It's an epidemic in the United States. There are a lot of people who are using opioids or abusing them, really. And unfortunately, many people dying from opioid overdose every day. Fortunately, there are treatments, and buprenorphine is a medication that can help people manage and reduce their addiction to opioids. And of course, in order to accomplish that, they have to stay in treatment, taking their medication and so forth, in order to eventually be cured. And so the problem is that, of course, some of them don't consistently take their medication or drop out of the treatment program or relapse, reuse opioids. And so this is a national problem, and the National Institute of Drug Abuse is interested in how we can better understand why some people succeed in these treatments and some don't. And even better, maybe, could we detect a relapse when it happens, or even predict that a relapse might happen? That's kind of a longer term goal. I'm not sure we'll achieve that in the immediate study, but that would be a tremendous outcome. So the main objective of the current study is to evaluate the feasibility of using digital technologies with these patients who are in treatment over 12 weeks to see if this is even feasible. And if it is feasible, then a second round of a project would expand the number of patients and try to actually maybe start doing interventions. In this case, we're really just measuring outcomes and collecting a lot of sensor data. So the secondary objective from a research perspective is to use 3 different kinds of digital data and see which of them actually seem to be useful. So first is EMAs. We ask the people questions several times a day about their drug use, about their medication, about et cetera. And we collect passive sensing data with smartphones and smartwatches, and we also collect all of their social media data for that period as well, because sometimes what they're saying on social media can be predictive of what they're doing in their medication. So as far as we know, this is the first time this kind of approach has been employed in an OUD population. with passive sensing, social media, EMA. We also get their EHR data from their medical records. And then we can have, ideally, moment by moment quantification of their treatment retention. Are they likely to stay in treatment? And are they adhering to their medication? And hopefully, are they not relapsing? So we've built smartphone apps and also using a Garmin smartwatch to collect a variety of sensor data. Any of you who have worked with smartphone sensing will recognize these sorts of things, pretty standard. And of course, it depends on Android and iOS and what they allow us to collect these days. And in the case of Garmin, we have to obtain Garmin's sort of initially processed data, not the raw data, from the Garmin website. And then the EMA data, we ask them several times a day, at least 3 times a day, and a lot of questions about their sleep, their stress, their degree of pain, which of course for many people is why they're taking opioids or why they started taking opioids, about their craving for drugs, about withdrawal symptoms or substance use risk related substance uses like smoking or drinking, about their mood, about the self-regulation, their context, where are you, what are you doing socially, etc. And if they have actually used substances, we ask them to tell us about that. Now, I mentioned also we're collecting social media data. This has also been quite tricky. Facebook, for example, is making it harder and harder to scrape this kind of information. So we've arranged a mechanism where patients who consent into the study and consent to share their Facebook and Twitter, etc., data will actually use our software to log in and download all that content from these sources so that we can archive it and process it. And then because we're working with Kaiser Permanente in California, these are patients in treatment, we are able to obtain their EHR data, some of it, about their medical treatment behavior over the course of the 12-week enrollment. And all of this information together will be, we hope, useful in inferring their and maybe predicting their treatment outcomes. So this figure, I'm sorry, is not very good. It's the best one I could get at the moment, but it's basically showing all the different components in the data flow, the Garmin smartwatch and the smartphone. The watch data goes through the smartphone to Garmin and then up to our servers. And then the participant will, at one time, or maybe 2 times, beginning and ending of the study, they log into their PC and download their social media data to our server. And then scrolling up here, the server then automatically issues them payment. They get payment incentives every time they sort of comply by the study protocol. And we also produce a dashboard that allow the research assistants. It's a pretty big project. There's hundreds of patients potentially involved, to keep track of all of the patients, participants, and all of their data flows, and if there's any problem, to call them, etc. So the kinds of outcomes that we're concerned about in this for people in this treatment is relapse, which of course in some ways is the worst case. They use a non-prescribed drug while they're in treatment for drug abuse. And that's unfortunate, right? Because that means the treatment is failing. Non-compliance, they're not taking their medication consistently according to the prescription, and that puts them at risk, of course. And non-retention, they might just drop out. These are all negative outcomes that we hope we can infer or predict. And at the moment, our primary focus is on relapse, and that means the research question specifically is estimating the risk, or if you will, likelihood of relapse over different time windows. Like, what's the likelihood somebody will relapse within the next day, within the next week, within the next month? And if we can be fairly accurate about that kind of prediction, that could be extremely powerful. It would allow, for example, the clinical team to maybe intervene in somebody who seems to be at risk. So there's been, not surprisingly, a lot of studies about opioid use and opioid use disorder before, and there's a lot of challenges that people face when they're going through this kind of recovery from opioid use. And so fortunately, I guess, in a way for us as the technology researchers, a lot of these have been studied already. How do you detect stress? Well, we talked about that a bit. How do you detect or infer anxiety, depression, mood, sleep, craving? there's a lot of work done on that, and we can build on that. And ideally, we can maybe adopt some of those methods, analytics methods, to produce intermediate inferences, if you will, and use those inferences to ultimately infer our top level goal about relapse. So we're really just getting going. We're in the sense that we're about to recruit subjects, I think, starting next week. We've been planning this for a year. But thinking ahead to when we actually have some data, we plan to build generalized models initially across the entire patient population, participant population, and using the standard sort of leave one subject out or leave one group out, cross-validation. But we're really interested in building personalized models that are trained on data from a person over time and then adapting to that person's treatment or behavior over time. And often the best way to do that is to start with a general model that's trained on a larger population and then retrain it in effect as the new data comes available. Another approach is a group-based model. So if you have enough data, you could say, you might determine, for example, that certain genders, males versus females, progress through treatment differs, and a model that's tuned for a gender might be more effective, or age groups, or ethnicities, or income status, or some other kind of static demographic data could be useful as a differentiator initially in terms of initializing that model. So the goal ultimately is to provide a deeper understanding of the treatment trajectory and to help the people who design interventions to maybe design more interventions that will be more likely to be effective because they understand why people relapse or when they relapse and what are the conditions that lead to that. And I hope we can also show that our models can detect or even predict these relapses, because that would be a huge opportunity to help these people. And so this then would open the way for JIDIs, just-in-time adaptive interventions, which is a mouthful, but it's a technique that's becoming more and more possible and popular. Just-in-time meaning you detect in the moment when something is happening to a person's health, and you adaptively choose an intervention according to that moment or to that person's history in a way that will help them change their behavior in whatever way is desired. So as I mentioned, this has been underway for quite some time. Showing the study preparation here from January to June. Actually, we started last fall, but the real main effort, I guess, has been in the last 6 months. And we're just starting recruitment. I think it's next week. We hope to have our first subject streaming data to us by mid-July. And it's a rolling enrollment. So we're planning for enrolling subjects right up through the end of January. They each participate for 12 weeks. And I think the target is 80 participants. And then the active phase, meaning recruiting and data, starting subjects, ends between September and April. And then the data lock, as they call it, basically NIH requires us to clean the data and then at some point say, okay, the data is here. This is exactly, it's all clean and ready to be analyzed and shared with others. And that should be done by sometime mid of next year. So this is a big project, as you can imagine, primarily at Dartmouth, including clinical psychologists, including data analysts and computer scientists and technologists of various kinds. And at IBM Research, that's Qinghua's team is, I would say, the primary analytics team. And then, of course, at Kaiser Permanente has the patients, and they are actually on the ground, as it were, recruiting the subjects and handing out the technology and helping with the data collection. I want to acknowledge the very bottom person on the Dartmouth list, Varun Mishra, my graduate student who made all these slides, and so I'm appreciative to him. So my final slide is just to acknowledge the various support from NSF and Health and Human Services, NIDA, NIH, et cetera. And of course, to emphasize that everything I've said here are my views and not necessarily theirs. And also to, at the bottom here, to show, to have links to the Amulet project, the Oracle project, our security and privacy project called THAW, and the two centers that I'm affiliated with, the Center for Technology and Behavioral Health at Dartmouth, which is the basis for the DTEC project, and the Center for Digital Health Interventions here in Zurich at ETH, which is has been my home for the past year on sabbatical. So with that, I'm done, and I'm really happy to have any questions that you might have.
Thank you very much.
So kind of how do you want me to handle the questions?
Yes, so we got several questions on Q&A windows. So let me unmute these people who asked questions. So first, we have some questions from Ashu. So let me unmute him. Oh, maybe I can. Okay. Ashu, can you speak up your questions?
Yeah, David, as always, thank you very much. Great talk. Just quick questions, and then I'll hand it to the other folks. Might come back with more later. On the Oracle project, could you comment on ability to differentiate drinking from eating, and if it's possible, do they make different sounds?
Yeah, that's a good question. So we've actually so far not tried to detect drinking. We've done some preliminary experiments, and unfortunately drinking does not produce enough sound, at least for our microphone in that placement, to be detected. If we had a microphone on the throat and we're listening for the sound of swallowing instead of the sound of chewing, then it would be maybe more possible. And some have taken that approach. Part of it is how you define eating. We actually spend a ridiculous amount of time looking for a definition of eating. If you want to detect eating as an engineer, your first question is, well, okay, what's eating? And the health literature is remarkably vague about this. Well, it's a meal or a snack. Well, what's a meal? What's a snack, right? So we define eating to be the process of taking food in and chewing and swallowing it. And so that does not include drinking, because you don't chew it. And it doesn't include chewing gum, actually, because you chew it, but you don't swallow it. So so far we've just defined it away, but my student Shengji, who has done the lead on the Oracle work so far, is now taking a different approach and is planning to, or hoping to, detect eating and drinking. So we'll see.
And then on the I think this was the third project on stress. Could you comment on whether stress is considered a binary state, like you're stressed or not, or is it something which is defined on a continuous scale?
Yeah, that's a great question. It is, I would say, inherently and intuitively continuous, right? That people are not binary. At least some of those people I know are kind of maybe that way, but the physiological response, which is really what we can detect, is definitely continuous. And so that said, in our study, our classifier was binary, stressed or not stressed. And so in the case of the lab tests where we induced stress, we essentially had a timer, and we said, at this time, we're going to start making you do math, or we're going to drop books behind you, et cetera. And in those moments, those minutes, you were stressed. And in other minutes, you were not stressed. And so then we produce a classifier, binary classifier, and compare it with those results. In the field, we asked the person, how stressed do you feel on a Likert scale, 1 to 5? And so we had to convert that into a binary, right? So I don't remember where the threshold was, but maybe we said 3 to 5 is stressed and 1 to 2 is not stressed. Ideally, I would personally like to see these algorithms produce continuous output, or at least like on a scale of 0 to 1, how stressed are you? Because I think that could be useful. The problem is right now, as far as I've seen, it's very difficult to get gradation other than binary accurately.
I mean, in this case, are we measuring heart rate variability related metrics, or is something different?
In our case, yes, we're looking at RR intervals specifically, which gives us, among other things, heart rate variability. Other people have used EDA, right? The electrodermal activity, the skin resistance, because when people are stressed, they get sweaty. And you can look at other metrics. The best one, the gold standard, is cortisol which can be measured in your saliva, but obviously as a continuous monitoring, unobtrusive sensor, that's not very easy to do. So stress monitoring to me is sort of a holy grail. The psychologists would love it, right? Because so much behavior is driven by stress, or stress is a result of some conditions which can be psychologically damaging. And so if we can detect it in real time, unobtrusively, continuously, that would be fantastic.
Right. Okay. Thank you. And I will let other folks ask questions. Yeah.
Okay, then let's move on to Manoji. So I will unmute you. Oh, is it working? Yeah.
Hi, so very nice talk. Thank you very much. I was wondering, or I missed it if you have already explained it. How do you convert the eating time? So what I believe is from your device, you just collect the time when somebody is eating. How that intake is converted to calorie intake?
Yeah, we don't attempt to do that at this point, but our goal was initially to provide the foundation for a broader set of capabilities, and that foundation is on a time window basis. Are you eating or not eating? Again, binary, right? And so we've done that as short as 3 seconds and sometimes 1 minute, and then we can aggregate periods of time over which you're. Because if you think about it, when you sit at a meal, you're not eating literally continuously. You take a bite, you chew it, you pause, you take another bite, you chew it, you pause. And so, but over the course of an hour, you're eating a meal, right? And so then the next question is, well, how much did you eat? Or, and then of course, in order to get calories, you also need to know what did you eat? And so even we've done some initial experiments with trying to estimate volume, actually weight, mass of food eaten from the sound. So we were collecting sound data, just like we always have, and we had different foods on scales. And so when you pick up food from this plate, that scale's weight changes, and we can measure that instantaneously. And then we can compute over time how much food of each food you have eaten. Unfortunately, the results so far are not very promising. Just from the sound, it's been very difficult to distinguish which of those 3 foods they ate and or how much. But that is something that is needed, right? And so far, it's not, with microphone only, not worked well.
Thank you.
Yeah.
Okay, then let's go to Tan, and after that we are going to Bishop.
Yeah, thank you for this very good presentation. I have a question about the Oracle project, David. I wonder, is it possible to actually use hearing aid and detect the chewing from the ear canal? That way you don't have to develop.
Yeah, that's an interesting question. Hearing aids have external microphones and internal speakers, essentially, right? They're listening to the sound from the environment, and then they're amplifying it and transmitting it somehow into your ear so you can hear. And so what's in the ear canal is not a microphone. And in fact, the sound that a hearing aid is designed to pick up is the external sound, the environment. And our contact microphone is the exact opposite. It's trying to pick up the internal sound and not pick up any environmental sounds. That said, there have been several projects that have looked specifically at how to measure eating behavior from the ear canal. And I can think of at least 2. And one of them used a microphone, actually essentially put a microphone in the ear canal. And another one measured the physical changes in the shape of the ear canal. Because when you chew, of course, your skin and your muscles move, and your ear actually changes shape slightly. And they were able to measure that. I've been personally trying to stay out of the ear canal. I want a device people will wear all day, and I don't want to plug their ears. I want them to be able to hear, right? Now, of course, teenagers these days always have stuff in their ears, and so maybe it wouldn't be a problem. to add that.
Thank you.
Then let's go to Vishal.
Yeah, thank you, David, for your nice talk. I had a few related questions for opioid uses relapse project. So on that particular project, how do you obtain ground truth of a relapse? So are these based upon the EHR data, and are these relapse events sort of a discrete event in time that it starts on a given day? And on a related question, do a particular participant have multiple instances of relapse, like a relapse then it goes off?
Yeah, that's a really good question. I believe, and again, it's a big project, and I don't know all the details of every aspect, but my understanding is that we will be asking them for self-report, both through the prompted EMAs, and also they have the option anytime of opening the app and saying, I just used a drug. And they will be encouraged to be honest, right? So we can, or hopefully will, get self-report. But then there will also be EHR data. So if that information about the drug use, the relapse, comes to the attention of the clinical team, then it would be presumably logged in the EHR and available to our team as well. It's entirely possible that somebody will relapse and then go back on treatment and then relapse again. I imagine that's unfortunately not uncommon. I'm sure it's also the case that there will be relapses we won't know about, right?
Yeah, thank you.
Yeah.
So I have a few questions. I think it's okay. So yeah, related to the final latest project about opioid. And so, which wearable sensor are you gonna use?
So it's the Garmin. I don't remember the model number. I could look it up, but it's a standard Garmin smartwatch.
Then also, I think, yeah, a lot of us have been working on, for example, detecting like stress or depression or anxiety moment. But I think the difficulty is still in like distinguishing, these events. Biologically, we might just see, high arousal or some changes in heart rate variability. But I'm just curious how your team is trying to kind of separate this event.
Yeah, that's a good point. And I think in some ways that's why detecting stress is so difficult, is that what we're measuring is arousal in some form, right? Often with heart rate or EDA. And there are a lot of causes for that. And even stress comes in at least two flavors, physical stress and mental or psychological stress. And so I wouldn't say that at the moment we are, other than trying to exclude periods of physical activity that might be an obvious generator of physiological responses like stress, other than that, I think we are essentially, we may be confounding other activities, other experiences that are not stress with stress. The problem, I think one of the reasons this is so difficult is that getting ground truth is very difficult. If I ask you, are you stressed? Well, people's perception of stress is not the same thing as actually being stressed. And so, I can only ask you so often, because otherwise you're going to make me go away, right? So it's very difficult to know whether your algorithm might actually be more accurate than the person, right? Because we don't have complete data for a person, and we don't have anything other than their perception to work with. So I'm not sure if I really answered your question, except to say this is a hard problem, and I don't think we have the answer.
Thank you. Also, another last question is: so you said you are planning to monitor this patient for 12 weeks.
Yes.
Then for example, for 80 people or 100 people, then how many relapse events do you expect, like within this?
Yeah, that's a really good question. How many relapse events? We're really unsure. I mean, these are patients who have opioid use disorder, who are in treatment for that disorder, and so I would imagine it will happen. But we are certainly expecting an extremely unbalanced data set, right? I mean, I hope for the patient's sake we see no relapses, but that will be, I think, could be a very big challenge for us if we want to infer or detect or predict relapse, and then there are very few relapses. It could be difficult. So we'll see. I think we'll find out. That's why this initial study is really a feasibility study in some ways. And one of the conclusions might be, in order to really collect enough data, we need a much larger sample. I don't know. We've also, one of the reasons the project is starting so late, I mean, we planned to recruit subjects in January, and here it is July. And a lot of the reason was bureaucratic IRBs and technology review committees, and I mean, unbelievable amounts of review of the protocol. But also then COVID hit, right? And so both the processing of those bureaucracies has slowed down, but also now we've had to adapt our protocol to the realities of COVID-19. And since the study is done in California, where there's a lot of cases, it may affect our ability to recruit and run the study. We'll see.
Yeah, thank you. Looking forward to hearing more about the project update. I think that's all of our questions, and I'd like to thank again Professor David Kotz for excellent talk and very interesting research topics. And also I'd like to thank everyone who joined our seminar today. And so this is the end of today's seminar. Thank you very much.
Well, thank you for inviting me, and thank you everyone for listening. I appreciate it and would always appreciate feedback. Thank you.
Thank you.